So I'm back and we can continue. So let me again recall our setting. So let E be a Banach space. Let it be a Banach space and consider a convex set C that is contained in E. Then we will show that then we have, and call it like a proposition. C is weakly closed, and I put it this way: if and only if C is closed. And we'll remember it. This is becoming an important statement. We will be using it at multiple occasions. So we know that in such a case, for the convex sets, the weak closedness and the strong closedness is the same. And we will repeat basically the proof that was presented earlier. So first of all, notice. So proof. Notice that since weakly closed sets are closed, so the implication, this implication, is evident. We need to show that if C is closed, then C is weakly closed. No, that's correct. Is closed, then it is also weakly closed. To do this, we just simply notice, so therefore, we need to prove that in such a case, that the complement and I put it like this, C with the C, so let me write what the complement means. We just take the C out of a closed convex set is weakly open. Okay, so let's begin. So take any point x naught that belongs to this complement, CC, any point, and put, I have here two sets, let's say put it like this, the set B will be just simply the set C, and the set A will be the set X naught composed of a one point. Now A, B are closed convex sets, very good. A is one point set, so it's compact. Therefore, we can apply the Banach strict separation theorem. Separation theorem. That means there exists a functional f belonging to E star, and there exists an alpha belonging to R, such that for every B is the convex C, so for every x belonging to C, I have here like this: f on x is smaller than alpha, and this one is smaller than f of x naught. F of x naught. So again, let's remember just in the previous segment, we just did the same. Instead of taking C, actually it was like we wrote a B. This is our B, so this is exactly the same situation. So there is no difference between this proof and the previous one. So I just simply can copy this little picture and show you what's happening here. So this is the set R. Here, what do I have here? I have here the number alpha. Here I have the value f of x naught. So that this is this value, this is this value, it's larger, so it is here. And then I also have those values, and they're on the left side. Okay, so that means those are the values f of c. And now, okay, it is possible to choose an epsilon such that that point here, this is epsilon, and that point, of course, it doesn't matter. For some epsilon larger than 0 is still larger than alpha. That means you can always say that let's say choose, put it like this, choose epsilon larger than 0 such that alpha is still strictly smaller than fx naught minus epsilon. 10, we have the C intersection, and I put it like this, f minus 1, and this will be f of x0 minus epsilon, and this will be f of x0 plus epsilon is exactly the same. And this set, again, we notice that this is this one is the neighborhood of x naught, which is of this type. You just simply have one element in this set, f, capital F, and this is epsilon. So it's an open basic. This is weakly open, basic neighborhood of x naught such that, and again, that this V f epsilon is contained in CC, which proves that CC is weakly open. And that actually finishes the proof of that statement. So we'll remember this statement. Let me make an important observation. We'll also write it as a theorem, because it's kind of a important fact. So let's write it down. Theorem. Let E and F be two Banach spaces and A from E to F a linear operator. Okay, so we write it down. 10 we have. Put here 2 dots and move a little down and say A is continuous. If and only if A is weakly continuous. Weakly continuous, and that means simply that A, maybe put it in red, so that means A belongs to the R. This is EF, that means it's a bounded operator, that's the same. And then this means simply that if you take E equipped with the weak topology, and then take F equipped with the weak topology, is continuous. So we have it. So let's do the proof. So suppose A is continuous. I'll write it down, bounded. So we need to show that inverse image of an open set is an open set. We can just simply show that inverse image of a basic weakly open neighborhood of certain point in the space F is exactly an open set in weakly open set in E. So assume that AX naught is equal to Y and consider the basic weak neighborhood and put it like this, V, and this would be F epsilon of Y naught. We will compute, and we have A minus 1, let's write it down, of this neighborhood, so put it like this, A, F, epsilon. So it is equal, so let's write it down. This is equal to the set of all x's belonging to E such that AX belongs to the V, and this is F epsilon. But that way, so let me write it down, start maybe a little earlier. So this is X is belonging to E such that for every F belonging to this finite set F, so let me recall this one is here F is a set in E in F star, and it's finite. sure that we do it correctly. And then we have here that this belongs, so that means I have here AX up, not exactly, like this, F, and this is AX minus AX naught. Yeah, this F is smaller than epsilon. This belongs to this set. That's by the definition of this F. So let me rewrite it. But that means the same. So let's write it down. X belongs to E. And then we have here for F belongs to the finite set F. I have here also F, and I put here A, and this will be X minus X naught smaller than epsilon. And then you can see, wow, what does it mean? This is evaluation. So this is evaluation. Just simply remember, you can evaluate the F on A of this particular value. So what do I get? This is the set of X belonging to E, and that one is F belonging to F, and I can write it down F first, and I put here A, compose with A, applied on X minus X 0 smaller than epsilon. So that means simply that here I can write it down. This is X belonging to E, such that for every F, put it like this, tilde belonging to F composed with A, so this is a symbol I am introducing, symbol. So this will be equal to the set of all values F composed with A, and this is F belongs to F. So that's, of course, is also belonging to E star. So that's a finite set. And then I have here that one will be equal to F tilde. And this will be X minus X naught. And that one will be smaller than epsilon. Which means simply that this is V again. V neighborhood, but this time is not of the point y naught. Here it is, here we have here the this is of y naught. So this was a neighborhood of y naught, and now we are getting a neighborhood of x naught, and this neighborhood will be simply, put it like this, F composed with A, that's the set F, F, like that. And this will be epsilon, it's basic, weak neighborhood of x naught. Oh, and yes, that means simply, so it is open in, and I put it like this, is E was equipped with the weak topology. Good. So we prove it. So now let's prove it other way. So, suppose now that A, and this is going from E weak to the F weak is weakly continuous. So now we understand that E and F are considered with the weak topologies. That means our weak topologies give it the structure of a topological vector space. We already examined this property, so we can in such a case, we can, okay, consider the following composition of maps. Consider the following composition of maps. Maybe I should say linear operator. So I say we start first with E, and everything is taken with the weak topology. So we should understand, I put here W to indicate that we cannot use the norm, you cannot use the usual arguments for showing that we have here kind of a continuity. It has to be done in the other way. So what do? I just simply say that this goes to exactly this space FW times FW. Call this operator T, and then I have another operator here. This operator is also going to the FW, and I will call this one T, call this one S. So what is the T? And take this composition. This is the composition, and this not nice composition. 1, 2. So take composition and STR, call it by R. So what is T? I take T and I see that T on X and put it like this. Y will be nothing else than AX, and this will be Y. Since T is just a product A times identity, A is weakly continuous, A is weakly continuous. Very good. So identity is evidently continuous in any case, so T is weakly continuous. So T is weakly continuous. On the other hand, also S, define this S, so let's define S on Y1, Y2 will be equal Y1 minus Y2. Also S, that since F is a FW is a topological linear space, so that definitely F is also weakly continuous. I emphasize, this is one of the first observations about the weak topology, that this is a topological vector space type of the topology, that it makes addition and multiplication of vectors by scalars continuous. Here we have the definition of this operator, so this is basically addition and one multiplication by -1. So definitely this is a continuous operation, because the vector space operations are continuous with respect to this topology. So it's continuous. So the operator and put it like this, R of x, y, and I can write it down. This is a x minus y, this is how it is given, defined, is also weakly continuous. Then, since the inverse image under R of a closed set is closed, So put it like this, r minus 1, and I take this, and I'm getting, that's exactly the graph of A, and the inverse image here. This is inverse image of the 0, which is closed, weakly closed, definitely. We obtained that GR of A is weakly closed. But on the other hand, that's a linear subspace. GR of A is convex, as a linear subspace is convex. Therefore, by our previous result, GR of A is also closed with respect to the strong topologies, to strong topology. Once we know that this is closed, so what is left? So therefore, by closed graph theorem, A is continuous. And we basically got it, so that means we finished our proof. We finished our proof, and maybe we have to look into the one more result, so namely, let me change the paper. Let me make another statement, which will be corollary This corollary is called the Mazur theorem. Let's formulate it. Let Xn be a sequence in a Banach space E such that this Xn is convergent weakly to a certain element X naught. Very good. 10. There exists a sequence Yn, and this sequence will belong to the convex hull of all these points Xn. N is equal 1, 2, and going to infinity, such that Yn actually is convergent strongly to X naught, strongly. So proof is kind of easy, observation proof. So put it like that. I just put it like this. Put. C, and I put here, is equal exactly the convex hull of this particular sequence. Let's Clear? You already know that this will be like a, maybe write it down here. This will be equal, maybe, union. Okay, m is equal to 1 to infinity, and this will be, I can put it like this, Cn. And what is this Cn? Cn, it will be set of all convex combinations. So I'll put it like that. This will be like a I equals 1 to n, and this will be alpha I, and this will be like x n I, such that sigma alpha I is equal to 1, I is equal to 1 to n, and alpha I are all larger equal to 0. So this is like a convex combinations of the length m, composed of the, of course, of the elements. Those are the elements of the sequence. So those are the elements of the sequence. Those are elements of the sequence. Okay. Okay. So we put it like this. C, and I take the closure is a closed set. Therefore, it is also weakly closed. Which implies that, okay, look at our assumption. Our assumption is here. That this guy goes here, this is weakly closed. If something is weakly closed, it's sequentially closed, so that means, which implies that x naught also belongs to the closure of it. And 10, so there exists a sequence yn, which is contained in C, satisfying the properties that yn is convergent to XO. Why? Because C closure, because okay, the C is closed, so that means this is a strong closure. This is element from the closure, so you can always find an element. Okay, maybe. Okay, I will explain why. Indeed, I write it down. Indeed. Let's put it like this. For every n larger than 0, there exists, because it belongs to the closure of C, there exists a yn belonging to C, satisfying the properties that x naught minus yn is smaller than 1n. Just by the definition that this belongs to C. But what is yn? And yn is equal to union of this Cn. N is equal 1 to infinity. So yn belongs to a certain element, certain subset yn. So that means yn is equal, I write it down, and I write it down like alpha I, and this will be n, and this is I is equal 1 to n, and this will be x and I, such that I is equal 1 to m, this is n, alpha I, n is equal to achieve this limit by, actually it's a strong limit. So, but not all the same elements, you have to change them to something else. So that's a nice result too. And that's basically the material for this particular part. And now, of course, let us do a couple of nice problems so we can understand that this is a lecture, and that means the lecture consists of the two things, theoretical part and practical part. Practical means simply we can expect some problems that we are supposed to understand and be able to handle. We are supposed to be able to solve them. So let's start with the problem number 1. So let E be a Banach space and A contained in E a compact set. But this is a compact set in weak topology. So I put here W, so you understand that this compact set is with respect to this. Write it down, you can pay attention to this weak topology. Weak topology. And you can also add weak topology, sigma E star, that's how we were also denoting this weak topology. Show that A is bounded, is closed, and bounded in strong topology. So proof is extremely easy. It is based on the principle of uniform boundedness proof. Because so maybe start with the little statement, since this topology, weak topology, is contained in strong topology, this implies that A is strongly closed. Why? Because it is a complement of a weakly open set, and weakly open set is also strongly open set, so this is a complement of strongly open set, means closed set. Moreover, since for every f belonging to the E star, remember, f, if I take f from E and consider this E to be equipped with the weak topology to R, this is continuous. Why? Because that was our definition of the weak topology. This was exactly the definition of the weak topology. Weak topology was the smallest topology that make all this functional from E star continuous. So this is continuous. So now, and since A contained in EW compact, I put here weakly, so you understand that this is not the same, compact. Thus, what do I get here? Thus, I'm getting here that f of A contained in R, continuous image of a compact set is a compact set, is compact, and thus, therefore, it is bounded. And if this is bounded, that means we just show, so for every f belonging to E star, we have that there exists a constant Cf satisfying the property larger than 0 such that for every x belonging to A, I have here the value f on x is smaller than Cf. That means it's bounded. That means we have this property, and that implies, so by principle of uniform boundedness, A is bounded. Okay, let's do the next one. Problem. Let E be a Banach space and let X n be a sequence in E such that the sequence Xn converges weakly to X naught. Show that and I put here like this, for y n equals, and this will be like a 1 over n, and I put here x1 plus x2 plus xn. We have yn converges to x naught. Solution. Something was walking on my keyboard. Solution. Okay, let's write it down. A simple fact. This is actually high school fact. High school fact. So we have the following. Simple fact. Simple fact. Let alpha n be a sequence contained in R, be a sequence such that alpha n converges to alpha 0 and put beta n exactly like we did it before. This is equal to alpha 1 plus alpha 2 plus alpha n. 10 we have that beta n also converges to alpha 0. Indeed. We can rewrite it down like that. So let me rewrite these things as follows. So first of all, notice that limit as n goes to infinity alpha n is equal to alpha 0. So by the definition, for every epsilon larger than 0, there exists an n such that for every n larger equal to n, we have here alpha n minus alpha 0 is smaller than epsilon. Okay. 10. Fix epsilon larger than 0 and assume that n is given by the formula star. So this is by the formula star. So we have here, and let me write it down, beta n minus alpha 0, so that's larger or equal to 0. So you can write it down, this is equal to 1 over n, and then I write it down, alpha 1 minus alpha 0 plus 1 over n, alpha 2 plus, minus alpha 0 plus bang, 3 dots, and this will be 1 over n alpha n minus alpha 0. Is it clear? No, maybe it's not so clear. Okay, 1 over n alpha n minus alpha 0. Okay, you have to check it out, I don't know. Smaller equal, and this will be absolute value alpha 1 minus alpha 0. And this one is over n plus alpha 2 minus alpha 0 over n plus. And let me write it down. For n larger than n, I take just this one. So I can something. So this one is alpha 0. So then you have here alpha n minus alpha 0. This is divided by n, and this is plus, and this will be alpha n plus 1 minus alpha 0 divided by n, and dot, and this will be alpha n minus alpha 0 divided by n. So I keep this one and check what I see. I see that I can rewrite it again, and this will be equal alpha 1 minus alpha 0 divided by n plus alpha 2 minus alpha 0 divided by n plus alpha n minus alpha 0 divided by n, and that one is smaller than epsilon. So I put plus, and this will be n minus n multiplied by epsilon over n. Continue. That is smaller than this is. Sorry. Somebody's not thinking. N minus n epsilon divided by n. Better, much better. So of course, notice that one is smaller than 1, so I can just simply rewrite it, put it like this, smaller equal alpha 1 minus alpha 0 divided by n plus alpha 2 minus alpha 0 divided by n plus, and this will be alpha n minus alpha 0 divided by n and I put here like this plus epsilon. So I can pass the limit, and by passing to the limit, we get back 0 smaller equal, and this one is limit, and this is n goes to infinity beta n minus alpha 0 is smaller equal. So what do I get here? What do I get? If this all goes to 0, this is all. N is fixed, so this must go to 0, must goes to 0, must go to 0. Doesn't matter what. Also, this is n, capital N is a fixed number, so this will be epsilon, and this will be for every epsilon larger than 0, so that means you obtain that. Now this is equivalent that limit n goes to infinity of beta n is equal alpha 0, and you just prove it. So clearly, in order to show this particular property of the sequences here, this property, so if you would like to show that one, this property, double star, so you just need to show the following. By the property, since yn converges weakly to x naught, if and only if for every f belonging to E star, we have here f of y naught is convergent strongly to f of x naught. So put it. Alpha n in such a case would be like f of xn. Beta n will be exactly f of yn, and alpha 0 will be equal to f of x 0, and the result follows from above fact. Done from the above fact. And let me check. I have one more quick one, problem number 3. Let E be a Banach space and C contained in E a convex set, can the weak closure of C coincide with the strong closure of C. That means simply C weak closure is equal to C just a closure. And the solution is very simple. It's all from the properties of the convex sets. So first of all, notice that here the things are quite easy to check, because if you see in both cases, if I take for example C, and if I take the C, and I can see that C is definitely here, Do you see this? It's contained in the weak closure, but simply C weakly closed is a convex set. So since and it is weakly closed convex set, so it is strongly convex set, strongly closed convex set, strongly closed convex set, because we know that if a closed set is closed convex set is weakly closed, it must be, if and only it is on, okay, closed set is weakly closed, sorry, convex set is weakly closed if and only if it is strongly closed. So that means in such a case we know that that one is strongly closed convex set, and that implies that definitely implies, so we can say that since C closure is the smallest closed set containing the convex C, so of course we are getting here that that one is contained here. That one is contained here. And vice versa. On the other hand, since so we got that this equality is satisfied. On the other hand, we also repeat this argument, so namely the same way, and by reverse argument, since C is contained in C closure, and that one is also and that one, sorry, and C closed, maybe I should, C closure, since C is contained in C closure, and this is again closed convex set and is weakly closed, yeah, because closed convex sets are the same as closed, weakly closed convex sets. So we also get that C weakly closed must be contained in here, because the weak closure is just simply the smallest closed set containing the convex set C, and that implies that we have both inequalities, therefore C closure must be equal to C bar. You see, there are a couple of little details missing here. For example, show that if C is a closed set, so the weak closure of a closed set is also a Here is this missing little detail. So let me write it down. C convex set. So this implies that weak closure is also convex set. So I can put it on your homework. Those are not difficult statements. So if you have that one, then of course this point here will be covered. So all the details will be covered. I have one more problem to do it. This problem I will do as the beginning of the lecture 3, and just to remind you all the related facts about the weak topology in the space E, and after that we'll start star weak topology on the dual. And for a moment, thank you.